Sure.
All right, good morning.
Good morning.
Are there any questions? All right, so we were getting ready to compost our pumpkins, and I decided to bring it and save it just to show you a different way to light the pumpkin and introduce a couple different reaction types we'll get to in the fourth and final unit of the class. What I have here is calcium carbide. I'll write all this down on the whiteboard in a second. Calcium carbide will react with water and produces ethine, more commonly known as acetylene gas. Oh, yeah. Now, the interesting part about this reaction is I can't put it out with water. That just makes more acetylene.
Do we have to worry about smoke or smoke detection?
No, I only put a little bit in there. Yeah, but it's really kind of cool. You get these little floaty soot bits. You'll see them kind of zipping around the room for the next 15 minutes or so. Acetylene, when we work out the balanced equation for acetylene burning in oxygen, it uses up a lot of oxygen. And so in this set of conditions, I don't have a good oxygen airflow, so it tends to give us a little bit more of a sooty flame. But it's got an interesting history to it. That's this guy right here. This is called a carbide lamp. And so the top compartment has water in it. And it's got this little metal handle that you can use as a dial. You can drip out different amounts of water. Bottom section, that's where the carbide goes. Some more carbide in there. Right there. Good. The carbide comes in the steel can because we're trying to prevent it from reacting with water from the air, humidity. So it'll just come together here. And Nevada, we should catch the lights for us. So if you worked in an underground mine pre-electricity, you'd get a whole canister of this carbide, put some water on top, make sure you grab your lunch. Head on underground, 8 to 12-hour shift. Light's pretty bright, actually, and particularly within the context. If you've ever been on a cave tour, you don't need a lot of light to get around. What are you doing over there?
Officer, I swear.
Now, the big limitation to this style of lamp is, of course, it's got an open flame. So if you're in for example, a coal mine, God forbid, coal itself is an incredibly complex organic material, and there's often a lot of methane, ethane, propane present. And so you'd have explosions because of the open flame setting off that methane, ethane, propane. It wasn't until the advent of electrical lighting that underground coal mining got a lot safer. One of the big things in favor of Powder River coal is the fact that it doesn't have to be dug out from underground. You take the top layer of dirt off, dig out the coal, and put the top layer of dirt back down. You don't have to do the underground mining, which introduces a whole series of additional safety issues. I'm just gonna let that go, see how long it goes. Nevada, if you catch the lights for us, please.
Yeah, I had a chem teacher who did something similar, but he set off the fire alarm.
Oh, that's where you,
Yeah, it was.
I try to go smaller.
And then literally the next day, another teacher thought he could do it again, but more safer, and the fire alarm went off again. The next day, it was stupid.
I have never set off. It sounds like a challenge, doesn't it? But no, I'm not going to. No, my plan is to avoid setting off the fire alarm.
Yeah.
But yeah, entirely possible. I have caught things on fire before. but I've usually been able to put them out before anything substantial happened. I had one time I was showing people how to use Bunsen burner, and the tube came loose from the Bunsen burner, and so it was actually spewing out flames from the tube. I just turned off the valve, and everybody was okay. No harm, no foul. All right. So I want to draw the big picture. You don't have to copy it again if you're feeling pretty comfortable with it. But just as a reminder, we can relate the moles of any two substances using a balanced equation. I'm going to take a couple minutes to talk about that balanced equation within the context of the calcium carbide that I just shared with you. But the bulk of our time today is just working on this relationship. 1 mole equals the number of grams on the periodic table. What's the relationship between how heavy and how many? That's really our focus today. We can also deal with solutions. We can deal with gases. And we use the same relationships getting into or out of moles. We just have to kind of do the algebra to rearrange the relationship, whether we're dealing with mass or solutions or gases. So that substance, calcium carbide, that I shared with you earlier, carbide is a polyatomic ion. It's not one of the ones that you had to memorize for the second exam. I'm not asking you to memorize it. I'm just sharing it with you since I brought some in. It's 2 carbons and a total of 2 extra electrons, 2 negative charges. So we can draw a bonding picture for this. Each of the carbons comes in with 4 electrons, and we get to count those 2 negative charges as electrons. We've got 10 electrons to work with. We can attach those 2 carbons with a single bond. That gives us 8 electrons left. 2, 4, 6, 8. And neither carbon has a complete octet. So I'm gonna have to share 1 pair of electrons from this carbon and another pair of electrons from this carbon. The result is a triple bond between the carbons and a pair of electrons on each carbon. Each carbon ends up with a -1 charge. It's got 1 extra electron compared to what it came into the bonding picture with. That carbide ion in the presence of water is what we call a base. It is able to pull hydrogens off of other things, notably water. So one hydrogen can grab the hydrogen from one carbon can grab the hydrogen from one water, one carbon can grab the hydrogen from another water, and the result is a protonated or hydrogen added version. We've got the 2 carbons, each with a hydrogen attached. We would call this ethyne, 2 carbons with a triple bond. Historically, it's called acetylene. Now, in each case, once you pull the hydrogen off, that gives you a hydroxide ion. Those hydroxide ions get together with calcium ions to make calcium hydroxide. The calcium ions dissolve in water, the hydroxide ions dissolve in water, but the calcium hydroxide, once it forms, does not dissolve well in water. That's a solid. These are both AQ for aqueous, AQ for aqueous, but if you put them in the same container, they precipitate out, they add together to make a solid that does not dissolve well. So one of the types of reactions we'll talk about in the 4th unit are combinations of ions that form solids. We call them precipitation reactions. Another kind of reaction we'll talk about in the 4th unit is when we have something that picks up or accepts hydrogen ions, we call it a base. If something gives up a hydrogen ion, we call it an acid. So in this case, the water is acting like an acid. It gives up a hydrogen. We don't think about water as being particularly reactive, but it turns out it is pretty reactive. It'll give up hydrogens. It'll pick up hydrogens. In this particular case, it gives up hydrogens. And then finally, that acetylene, if we write its formula as C2H2, that'll react with oxygen to make carbon dioxide and water. This is what we refer to as a reduction oxidation reaction. Specifically, this type is referred to as combustion when things burn. Now, of the equations so far, this is probably the most challenging to balance. And we just kind of go back and forth. We got 2 carbons on the left, so we'll need 2 carbons on the right. Got 2 hydrogens on the left, 2 hydrogens on the right, so that one's okay. That gives us 2 times 2 is 4, plus another one makes 5. We got 5 oxygens. The way I could get 5 oxygens is to multiply by 5 halves. 5 halves times 2 is 5. That's not very appealing. We don't like to have half molecules. So instead, I could double everything. 2 of the acetylenes plus 5 of the oxygens makes 4 carbon dioxides and 2 waters. I double check everything. 4 carbons, 4 carbons, 4 hydrogens, 4 hydrogens, 10 oxygens. 8 plus 2 makes 10 oxygens. Now, for the third exam, all the equations will be provided, but they may not be balanced. You always want to check to make sure the equation is balanced, but it'll be provided for you. As we move into the 4th unit, we'll spend more time introducing you to acid-base reactions, precipitation reactions, and reduction oxidation reactions to give you a chance to try to predict your own outcome. So as we look at when things get together, what are the kinds of outcomes that are possible? And we use 3 types of reactions to kind of get us there. Questions about the big picture?
Sheridan said she was trying to get into Zoom and it won't let her.
Thank you. I just saw her name pop up. I appreciate you letting me know, though. Sheridan, thanks for joining us. We were just looking at the big picture and then talking about different types of reactions related to a demonstration I did, and it's recorded in the video for you to look at a later point. So our time today, looking at this relationship between mass and moles, between how heavy and how many for one substance. As we move through the 3rd unit, the first question is always going to be, are we talking about one substance and describing it in different ways? Or are we talking about 2 substances where we have information about one substance, we're asked about how much of another thing is going to be involved? For today, we're just talking about one substance at a time, no balanced equations. How do we describe how heavy something is versus how many there are? So I'm going to borrow that acetylene gas that we just made, C2H2. Using the periodic table, how many grams of acetylene are there in 1 mole of acetylene? As soon as you think you have a number, holler it out.
26.
26, good job. Each of the carbons is 12 times 2 is 24. Each of the hydrogens is 1 times 2 is 2. 24 plus 2 equals 26. So let's look at that number in a little bit more detail. So if I have 1 mole of this acetylene, C2H2, The little number is saying I've got 2 moles of carbon atoms. And I've got 2 moles of hydrogen atoms. I can convert those into grams. 12 grams of carbon per mole of carbon. 1 gram of hydrogen per mole of hydrogen. Now you kind of already know this, that in 1 mole of C2H2, there have to be 24 grams of carbon and there have to be 2 grams of hydrogen. You're kind of doing that originally to get the 26. What I want to do is look at that 24 and that 2 compared to the overall total. 24 grams out of 26 grams times 100 and express it as a percentage. 24 divided by 26 times 100, 92.3% carbon. And 2 out of 26, 2 grams out of 26 grams times 100. Say 7.7% of the mass is due to hydrogen. So we can describe a substance based on how much of the mass is coming from each element. What I'd like to do is try to go back the other way. If I knew from experimental data that 92% of the mass of a substance is due to carbon and 7.7% of mass of a substance is due to hydrogen, how do I work out what the formula is? How do I work out the little set of symbols and numbers that we've been using so far this semester to describe that substance? And the answer is in this idea of the mole. That when we talk about these percentages, we're talking about how heavy. I want to get to how many. Now, the challenge with a percentage is you need to take a percentage of something. And so I'm going to pick 100 grams. I pick 100 grams because it makes percentages easy. If you take 92.3% of 100, what's the answer? 92.3. I could use any mass material I want, but it makes a lot easier. It makes it a lot easier if I just use 100 grams worth of material. If I have 92.3% of my mass is due to carbon, with 100 grams, I've got 92.3 grams of carbon. And I've got 7.7 grams of hydrogen. What I want to do is pretending that I don't know the formula is C2H2. Can I get to a description of how many atoms of carbon and how many atoms of hydrogen? I go back to the periodic table. Every 1 mole of carbon has a mass of 12 grams. Every 1 mole of hydrogen has a mass of 1 gram. That's 7.7 moles of hydrogen. And 92.3 divided by 12, that's 7.7 moles of carbon. So I can write the formula C7.7, H7.7. And I realize that decimal atoms don't make any sense. So I divide through by the smallest number. In this case, neither number is smaller, so I just use the same number here, 7.7. And I get 1 carbon for every 1 hydrogen. So what we call the empirical formula. The simplest ratio. So by itself, it doesn't get me to the actual formula because it gives me the simplest ratio. The word empirical is related to the word experimental. So based on experimental data, what we can say is there's got to be 1 carbon for every 1 hydrogen. But if we're told from another experiment that the molecular weight, if it has to be 26 grams per mole, and this stuff is 12 plus 1, this is 13 grams per mole. What do I have to multiply 13 by to get 26? 2. So what that means is I must have a 1-to-1 ratio, but I must have twice as many carbons and twice as many hydrogens. C2H2 gets me to the right molecular weight. When we have the actual ratio, we refer to that as the molecular formula. It's the actual ratio. If we consider the molecular formula for glucose, C6H12O6, that's its molecular formula. If I simplify the 6 to 12 to 6 ratio, I get CH2O. That's the empirical formula. It's the simplest whole number ratio. 1 carbon for 1 water. Glucose belongs to a class of molecules that we refer to as carbohydrates. And it's the fundamental building block for all carbohydrates that we eat. So whether you're eating starch in the form of spaghetti, bread, rice, potatoes, starch is a key source of energy for biological systems, us included. They are referred to as carbohydrates because at their simplest ratio, it is 1 carbon for every 1 water. Carbohydrate. And the empirical formula, carbohydrate, 1 carbon for every 1 water, speaks to the origin of carbohydrates. Carbohydrates come from plants taking the carbon out of carbon dioxide and adding water, putting those together in a new bonding arrangement to store solar energy. That same solar energy is what we take advantage of when we eat carbohydrates. So if you would please, how much does 1 mole of glucose weigh? Take a second. If you have a number, holler it out. Let's see if it agrees with some what other people are coming up with.
$180.
180. Well done. Good job. So we've got 6 carbons at 12 apiece. That's 72. We've got 12 hydrogens at 1 apiece. That's 12. And we've got 6 oxygens at 16 apiece. That's 96. Adding those guys together, 0 will carry the 1. 7, 8, 9, 9, and 18. 180 grams per mole. So if I have 2.5 moles of glucose, how many grams would that be? And if I have 15 grams of glucose, how many moles would that be? So you've got the conversion factor now. 1 mole is the same as 180 grams. How much would 2.5 moles weigh? How many moles would be present in 15 grams? We're gonna use the same conversion factor in both cases. The difference is how we set up the conversion factor. If you want to get grams, you put grams on top. 1 mole goes on the bottom. In this case, for glucose, it's 180 grams per mole. The unit moles cancel. End up with 450 grams worth of glucose. Questions on that conversion? In the second one, we're using the same numbers. We're just swapping where they are in the conversion factor. I want to get rid of grams, so it goes on the bottom. 1 mole goes on top, and it's glucose, so it's always 180 grams per mole. 15 divided by 180, 0.083 moles of glucose. We're always going to use 1 mole, and the number is always coming from the periodic table. All right, we're going to do a couple polling questions.
And like when she explained it like that way, I was like, okay, I do this.
Okay, so for my Zoom folks, make sure you log in. You can do the polling from home. What is the mass of 1 mole of sodium chloride? You'll notice here I wrote mole, MOL. That officially is the abbreviation for chemists. If you want to abbreviate MOLE, it's kind of quirky. The lowercase m is used as an abbreviation for another unit of concentration that chemists use. MO is awfully similar to the chemical symbol for molybdenum. And so chemists agreed MOL would be the way to shorten it. You can use the E and any other words you want. Take the savings and go make use of it. What is the mass of 1 mole of sodium chloride? Okay, take another 15 seconds.
Wait, hang on, I'm still watching into it. Don't go
Okay, all right. Got it. Are you okay?
Yeah.
No. All right, I'm go ahead and close the poll. Good job. 58.
23 for the sodium, 35 for the chlorine. For the purposes of our class and the exam, round to the nearest whole number. You don't have to have any decimal points, just round to the nearest whole number. The only time where the decimal points really come in handy are times like in lab, especially if you've got a situation where you've got really sensitive or small amount of material. But for our purposes, Chem 1000, just go ahead and round to the nearest whole number. All right, what's mass of 1 mole of sodium oxide? Now, what's the biggest difference between this question and the last question?
Oxide.
So oxide, in terms of a detailed difference would be the oxide, but more generally, what's different about this question?
We have to figure out the
You
formula.
have to figure out the formula, yeah. So that whole naming thing and the index cards, you get to use the index card again because you need the name to figure out the formula. And if you don't do the formula right, you can't get the weight from the periodic table correctly. So what is the formula for sodium oxide? How much is 1 mole of sodium oxide weigh? What's charge on a sodium ion? +1. What's charge on an oxide ion?
-2.
-2. Okay, I'm gonna go ahead and close poll.
So for the next test, can we make a new note card and then also use our old note card?
Got to use the old note card.
And that's it?
That's it.
What? Okay.
Yeah. So the naming is a human invention. And it's so arbitrary and all over the place that I want you to have the index card. But the calculations we're doing, these are patterns that are fixed for all of matter that are not arbitrary based on human conversation. So you need to be able to do the calculations. But I want you not to have to worry about the names and the formulas. So you can write down anything naming formula stuff you want to write down. And you can keep that on your index card.
Oh, we won't need to like know like are we still having like know the alkene and like that stuff?
Yeah, so I might ask you a question. How many grams are there in 1 mole of butane? And so you need to know what butane looks like. It's C4H10, 4 carbons, 10 hydrogens.
Okay,
So your index card should have butane on it.
yeah.
So you just look at your index card. Oh yeah, butane's 4 carbons, 10 hydrogens, and you're off to the races.
Okay.
Yeah. Good job. 62 grams per mole, 23, 23, and 16 for the oxygen, 62 grams per mole. All right, so now adding another piece, what if we're not dealing with 1 mole of material? What if we're dealing with something else? Got the calcium carbonate, got to work out its formula, figure out how many grams are in 1 mole, and then I'm asking you for the mass of 0.25 moles of calcium carbonate.
Hang on, it kicks me out. Did not move on.
Let's charge on a calcium. 2 plus. What's a carbonate look like? CO3. What's the charge? 2 minuses. So we've got equal and opposite charges, so they just go together. Let's take another 30 seconds. 15 seconds. Only got one more.
It's not me, I did it.
All right, I got everybody. Good job. 25 grams. So officially, the conversion factor would look like this. You got 0.25 moles of calcium carbonate, and it's 100 grams per mole. 25 grams. Now, at this point, this is just practicing the skill of converting from one thing to another, recognizing what the conversion factor is based on the formula, and then setting it up so you either have grams on top if you want to go to grams, or in this case, in this case, grams on top to get to grams, or in this next case, moles, 1 mole on top so you can get to moles. The importance of these skills are when we start to actually tie things together. So if we tie a description of a substance from how heavy to making a solution with it to getting into the gas state, or if we've got a chemical reaction trying to get from how many of this thing to how many of that thing. How many moles are in 70 grams of silver chloride? Let's charge on a silver. +1. Good job. Let's charge on a chloride. -1. +1, -1. They go together. AgCl. Take another 10 seconds. Okay, I'm going to close poll. Good job. Correct answer C. You guys are doing great. 70 grams. Silver chloride. Silver is 1/8. Chlorine 35. That's total 143. I want grams to go away. So 143 grams go on the bottom. 1 mole goes on top. Round it to 1 significant digit. That's 0.5 moles. Correct answer C. All right, which of these contains the largest number of particles? Is it 4 grams of helium, 20 grams of neon, 40 grams of argon, 84 grams of krypton, or do in fact each of these contain the same number of particles?
no, that's what I was thinking.
All right, let's take another 45 seconds. Oh, yeah, definitely. Right, we could, you set it up as a conversion factor. So you'd say, okay, I want to get to moles. Every 1 mole of helium has a mass of 4 grams. So I got 1 mole of helium, because when we talk about the number of particles, we're talking about how many moles. That's what the mole does for us. It tells us how many particles. 1 mole is the equivalent of a dozen. It's a really big dozen for chemists, 6 times 10 to the 23rd. I won't ask you to know that number on the exam, but it's a fixed number of particles. I take another 15 seconds. I'm going to go ahead and close poll. Go ahead and close poll. Correct answer is E here. If I go to the periodic table, 1 mole of neon is 20 grams. So that's 1 mole of neon. 1 mole of argon is 40 grams. That's 1 mole. 1 mole of krypton, that's 84 grams. I've got 1 mole of krypton. They all contain the same number of particles. They all contain 1 mole worth of material. The krypton's heavier because each krypton atom comes with more protons and neutrons, so it's going to have more mass. So it's like comparing a dozen paper clips to a dozen donuts. There are 12 things, but the donuts are just bigger and heavier. So the total mass of the donuts is a larger value than the mass of the paper clips.
So do you say like the particles is equal to like mole, like the number of moles?
The number of particles is equal to the number of moles. Yes. The word mole is just our unit. It's our name for how many things are present. It's a way of counting the number of particles. All right, we got one more here. What is what percentage of calcium carbonate's mass is because of oxygen? What percentage of calcium carbonate's mass is due to oxygen? If you double check your notes, just a few seconds ago, I asked you about calcium carbonate, so you already should have its formula written down.
It's mighty bold of you to assume.
Nice.
I think so. Hey. Your first school.
Let's go for another 20 seconds. Ooh, getting closer than that.
2 years of chemistry.
All right, I got everybody. Let's close it. Correct answer is B. Good job. So calcium carbonate is CaCO3. 40 for the calcium, 12 for the carbon, 3 times 16 for the oxygen. That's 48. The total is 100. 48 divided by 100 times 100 works out to 48%.
I mean,
Questions? All right, folks. So when we get back together, wait, I almost forgot. Oh my goodness. School District 2's added an extra day off on Friday. So there is no lecture on Friday. I'll post another little mini lecture for you guys. So there is no lecture on Friday. I'll send out an announcement to remind you. I will see you next Monday. Next Monday, we'll keep working on mass mole relationships and then extend it to a second substance. Look at a chemical reaction similar to what we did in lab, both this week and with the baking soda lab. All right, folks, have yourselves a good weekend. If you have any questions, anything you need help with getting the lab done, make sure you send me an email. Otherwise, I'll see you all on Monday next week.
Thank God that kid's in our class. Stealing's bad.